In section 2.7, we talked about one-to-one functions and their inverses, because I'm not paying attention. Anyway, I'm going to make this a little bit simpler than what we did in the notes. One-to-one functions are functions whose inverses are also functions. Because just because you have a function doesn't mean when you graph its inverse or you find the equation of its inverse that it is also a function. Now, if you have a graph and you're trying to determine if its inverse has a function, we use something called the horizontal line test. So, for example, if I gave you a quadratic equation, if you were to use the horizontal line test, you would determine that its inverse is not a function. Therefore, the function is not one-to-one. But if I instead gave you this graph, let me make this look nicer. This graph, which is the graph of a cubic function, if you were to do the horizontal line test, the horizontal line test would hold true. Remember, the horizontal line test works like the vertical line test, except we use it to determine if inverses are functions or if functions are one-to-one. So, not one-to-one. This one is one-to-one. So the easiest way to determine if a function is one-to-one is by graphing it and performing the horizontal line test on it. Then we talked about the inverses of functions. The way the inverses work is when you have a function, you have an input, and it results in an output. Its inverse turns the output into an input. So, if I gave you a problem and I said, all right, f of 1 is 5, f of 3 is 7, and f of 8 is negative 10, and I said find the inverse of 5, you would tell me the answer is 1. Because when the input was 1, the output was 5. So for the inverse, the output becomes the input, and the input becomes the output. This is our representation for inverse. It is pronounced inverse of f, or f inverse. It is not pronounced f to the negative first power, because it is not an exponent. It is just a representation, meaning inverse. That's it. So then if I said, well, what's the inverse of 7? You would tell me the answer is 3. And if I said, what's the inverse of negative 10? You would tell me the answer is 8. Pretty simple. The inverses, the outputs become the inputs. Let's do another problem and determine if two functions are inverses. Two functions are inverses if you do a composition of functions where you put the inverse into the original function and the simplified answer is x. Or if instead you compose the original function into the inverse and you also get x, then these are said to be inverses of each other. Here's the kicker though. They have to simplify to be x, not something else, not x plus 2, not 15, and it doesn't matter if when you simplify them they both have the same thing. They are only inverses of each other, inverse functions of one another, if the composition of functions in both directions is x. So if I tell you that f of x is x to the third, and g of x is x to the 1/3, we would determine if they were inverse functions of one another by performing f of g of x, which is going to be x to the 1/3 being put inside the third. This is the property where the exponents get multiplied. And then we would perform g of f of x. We would put f of x into g of x. But the exponential property is the same. You would multiply them, and 3 times a third is 1. So these are inverse functions of one another. However, if I had given you something like this, and I said f of x is equal to 2x, and g of x is equal to x plus 3, when you go to do a composition of functions, f of g of x would be 2 times x plus 3, which is 2x plus 6. I didn't get x. I can already tell you that they're not going to be inverse functions of one another, but I'll prove it to you by doing the other direction. When you plug f into g, you get this. They are not inverse functions of one another. Now, if you have a function and you want to find an inverse, there are some rules for finding inverses. First, you would write y equals f of x. Remember, f of x is the same thing as y. The second thing you would do is you would solve for x. And then, after you were done solving for x, you would interchange x and y. This would result in the equation of the inverse. So let's try this out. I want to find the inverse of f of x equals 3x minus 2. The way you find the inverse is first, you change f of x to y. Then you solve for y. You solve for x, you add 2, you divide by 3. And then you interchange x and y. And this is the equation of the inverse. Let's try it again on something a little more complicated. I want to find the inverse of x to the 5th minus 3 over 2. So first you would make f of x y. Then you would solve for x. First you would multiply by 2, add 3, and then you would take the 5th root of the other side, or raise it to the 1/5 power. And then all you would do is interchange x and y. And this is the equation of the inverse. Even if we have a rational function, we can do this. It's a little bit trickier, but we can still do it. We're going to solve for x, and there's multiple x's in here, so we're going to have to find a way to combine this so that there's only one x. Well, this is what I'm going to do first. First, I'm going to multiply over here. And then I'm going to distribute. And then I'm going to get my x's on the same side of the equation. So I'm going to subtract the 2x. And then I'm going to add that single all by itself y to the other side. Now the reason I did that is because now I can factor x out of the left-hand side. And notice that now I only have one x in the problem. And now all I have to do is divide the other side by y minus 2. Now I solve for x. And the last step is to interchange x and y, and then that is the equation of the inverse. Now remember, another thing you got to watch out for when you're doing these types of problems is that sometimes there is a domain. Not only can x not equal 2, because then the inverse would not be defined, x can also not equal 1 because of the domain from the original function. Last but not least, when we did this in Algebra 1 and Algebra 2, we talked about the graph of an inverse function. The graph of an inverse function, very easy. It's the reflection over the line y equals x. Because in the coordinate plane, the line y equals x, which looks like this, when you reflect a graph over the line y equals x, all you have to do is take the x and y of the original ordered pairs and flip them. So this ordered pair is at 2, 0. When I reflect it over y equals x, it's at 0, 2. The next one is at 3, 1. It's going to be at 1, 3. This one is at, let's see, 1, 2, 3, 4, 5, 6, 2. It's going to be at 2, 6. Let's see, which is going to be up here. And there's your graph of the reflection. It's a reflection if you could pretend like you fold a sheet of paper over that dashed line and the one side of the graph lies on the other. So if you can graph a function, all you have to do to reflect it is take the ordered pairs on the graph and switch them. Just a reminder, don't forget about domain restrictions. This blue line has a domain restriction of x is greater than or equal to 2. The domain restriction on the red graph, x has to be greater than or equal to 0.